Welcome, everybody. This is Srivastava. We are happy to have Srivastava from TTIC joining us. Shashank is a grad student at TTIC working with Madhur Tulsiani. Shashank works on an exciting area of coding theory, the applications of SDPs and some of SPES. He was working on some of the recent work, plus decoding of standard codes from distance certificates. He's, by the way, he's around for today and tomorrow. So you're going to and he'll be filling in the visitor's office.
Also new results about this decoding of standard codes, some other codes. This was based on joint work with Fernando, who's at Berkeley right now, and Madhur, who's at TTIC. Let's start with basics of codes. Code is just a subset of 0, 1 to the end. For now, let's say we are dealing with binary codes. The traditional usage of codes has been for communication, where we want to transfer k bits of information. We encode it into another string byte. And this string byte is passed through a noisy channel. And the hope is that even if this string byte is corrupted to a byte delta, as in some bits are flipped from 0 to 1 or 1 to 0, then because there was some redundancy added from byte from x to byte, we can still hope to recover x from byte delta. So one desirable property of a code would be that these bytes that we encode x's into should be somewhat spread out. The code C is called linear if it is a subspace of F2 to the n. The most important two basic parameters of a code are its distance. As we discussed before, distance is directly related to how much error correction the code can do, and its rate. Distance is about how spread out the code is, while rate is about how well packed the code is. And there's always tension between these two parameters. So if this was our entire space, code words would look like these spread out set in the space. If we had a particular byte and the corruption was such that we were still in this yellow ball, then we would at least hope to recover back y and from y back x. And this ball, at least if the radius is less than delta over 2, then these balls don't intersect for different code words. So we can hope to do unique decoding in this case. Once the number of errors exceeds this delta over 2 unique decoding threshold, then the balls will begin to intersect and we have to resort to what is called less decoding. Okay, so what happens when the number of errors exceed delta over 2? The hope is that, okay, maybe it's no longer just one code word around that code word, but it's still polynomial. If it is exponential, then it's hopeless algorithmically to do anything. But at least if the number of errors is such that the list size is polynomial, then we can look for algorithms. So this list of code words, this will keep coming up during the talk, and I'll call this list of code words around the corrupted code word. What the classical Johnson bound says is that there exists a function j of delta, which depends only on the distance, such that up to j delta, if the number of errors is up to j delta, then this list size is bounded. So up to delta over 2, of course, this is true. So the j of delta has to be at least delta over 2. And it's always true that j of delta is strictly between delta over 2 and delta. So there's always something non-trivial you can say. What is the algorithmic task? You have to find this list. And in this talk, we'll always be dealing with questions that are under j of delta. So combinatorially, the list size is always bounded. The only question is algorithm.
So when you say polynomial, it's polynomial in n.
A polynomial in n. So the total number of code words can be exponential in n. And the non-trivial part is that the list size is polynomial in n. In fact, if you are epsilon inside j of delta, then it's actually constant depending on epsilon. List decoding is kind of needed if we want to do information theoretically optimal error correction. That is, if we want to achieve list decoding capacity, etc. And it has also had other applications to complexity theory and pseudorandomnness, etc. We'll not go too much into that. Let's look at the specific code that we are dealing with today. It's something called Tanner code. So Tanner code is defined using sparse expander graphs. So let's say we have a bipartite expander graph with n vertices on both sides, and the degree is d on both sides. code words will look like 0, 1 assignments to edges. So each edge gets a 0 or 1 label. So each edge will either be 0 or 1, subject to the constraints that every local view from the left side and from the right side, there will be d bits visible, and that local view should be in some inner code C0. So C0 has block length d. And if we look at these d bits around a particular vertex, then these d bits should be in some code C0. Likewise, so there will be a total of 2 and many constraints of this form. And if this local code is a linear code, you can do constraint counting to say that there's still a lot of code words left in the global code. Okay, so in the seminal work, Sipser and Spielman showed that if the local code had distance, fractional distance normalized, fractional distance delta 0, then the global code, which is of block length n times d, will have distance delta 0 times delta 0 minus lambda. For those of you who know, if you just take this to be the complete bipartite graph, this would become tensor code, lambda would be 0, and then this would just be the tensor code. Some attractive features of this code is that one, that it is LDBC. So you get an infinite family of growing infinite family of codes that are LDBC. Just by taking infinite family of expanded graphs. And it is also like the source of many linear time decoders. This code has linear time decoders that can then be fed into other coding schemes to generate other linear time decoder codes. Okay. What about decoding time codes? So this is the distance delta. Sipser and Spielman in their original paper gave an algorithm that could correct roughly delta over 48 errors. And this was improved by Zimmer to delta over 4 with a particularly beautiful decoder, with alternating decoder. And it was further improved to delta over 2 by Roth and Skacek. And remember that delta over 2 is precisely the unique decoding threshold. So going beyond delta over 2 would require less decoding.
So delta is just a bound on the.
Yes, that's the best bound we know.
No, wasn't there a recent paper that showed that?
That's expander codes. That's a different kind of expander code with vertex expansion. Here we are dealing with spectral expander based codes.
But those results don't carry over to this version. They show that you can do much.
Yeah. So the distance improvement there is really good, but I think that is only applicable for vertex expander based things. So spectral expander don't give such strong vertex expanders.
Okay.
Okay. And as we discussed before, we do know that up to j of delta, there is bounded list, so at least we can hope for polynomial time algorithms. And our main result is to give a list decoding algorithm up to this Johnson radius. So if the inner code had distance delta 0 and the graph is a lambda expander, then we can decode up to radius j of delta minus epsilon in time that has 1 over epsilon to the 4 in the exponent, still polynomial. So to complete our picture.
Sorry, what is D here? D is the
degree
of the expansion.
So you should think of this as a growing family of graphs where D is held constant and N is increasing.
In particular, your algorithm does not get the list decoder for tensor codes up to the
no.
D being.
Yeah, there D would be pretty large.
Okay.
Here we are always thinking of D as being constant, and
Okay.
like in fact, like we probably can't even handle D being logarithmic.
But this is the caveat of the algorithm, or in the code itself?
I mean, for tensor codes, we know of other algorithms that can directly do well through sampling, etc.
Okay.
But this is geared towards constant degree. Okay, why care about this decoding time codes? Well, first of all, given that the decoder progress has been stalled at delta over 2 for a while, seems like going from unique decoding to list decoding requires new ideas in terms of algorithm design. most list decoding algorithms that we do know of work for algebraic codes, so Reed-Solomon codes, etc. And in Cannon codes, there's not much of algebraic structure to work with. And Cannon codes are also the source of linear time decoders. So if we really want to construct linear time codes such as list decoding capacity, etc., we should look at Cannon codes closely. But of course, our algorithm is nowhere close to linear time.
Sorry, this is the first such theorem, or
For list decoding, yes. What are the techniques? The first one is a new, somewhat different algorithm-friendly proof of Johnson-Baum based on a statement that we call the covering lemma. It's just a purely geometric statement. Next, we bring in the proofs to algorithms paradigm for codes that have been used for CSPs, etc., based on sum of squares and so on. Where if you have a right proof, then that directly yields algorithms. We'll see this in more detail. So essentially what I'm saying is that if the distance proof is made up of certain local properties, in this case, by local I mean, let's say D, where degree D is constant. So we have to look at D things at one time. And the local to global step was done by spectral expansion. Then that would directly yield a list decoding algorithm up to corresponding Johnson-Baum. So sometimes it could even be that the true distance is different and we have a poorer distance proof that we can fit into this framework. And then we get a list decoding algorithm corresponding to the Johnson-Baum of that distance.
sorry, so this thing you're saying that this will work beyond Cannon codes. This
Yeah, so we'll see a few examples of this, not just Cannon codes. But this is more or less a paradigm. I think there's still details that will have to be figured out. And it's not the first time that convex optimization based techniques have been tried for decoding. There have been works on LP decoders for Tanner codes, but those only work when the output was integral. List decoding is not very compatible with integrality. In fact, you want your solution to have everything about all the list elements. And we kind of give the first rounding algorithms when it comes to convex optimization based techniques for decoders. There are time limits. So let's start with the covering lemma. And this will essentially be a different proof of Johnson-Baum, which I think some of you will find interesting. And it's just a geometric statement, not much to do with codes. So if we are given a family F of unit vectors, potentially infinite, and another unit vector G, such that every vector in the family has somewhat large inner product with G. Then there exists some G prime in the convex hull of this family F, such that G prime also has large inner product with F. So G was completely arbitrary, but G prime has a bit more structure. The loss is that we went from inner product alpha to alpha square. So if my family looked like this, and this was G, then I can find some G prime inside the convex hull, such that G prime has large inner product with all the family vectors. And in fact, like G prime might not have unit norm. G prime might be inside the unit form. And the proof is just to take the smallest L2 norm vector in the convex hull. If it doesn't have large inner product, then you can just use the certificate that it doesn't have large inner product to lower the norm further. Okay. Is the statement clear? Okay. Let's try to use this.
Can you go with the?
Yeah.
I mean, I've seen this before. It's still getting.
No.
So, so suppose you pick the G that has the smallest norm.
G prime.
sorry, you pick the G prime within the convex hull that has the smallest knob.
Yes.
Okay, and then what do you do?
That G prime should already have this property.
Okay, so why is that?
If it doesn't, then let's say there is some F that violates this property.
Yeah.
You can take a convex combination of that G prime and this violating F and optimize for the right convex combination. And you can show that it was not the minimal one to begin with.
Where are you using hypothesis then? That for all F, that there exists such a G.
Where am I?
So the argument you just now said, I didn't see. The hypothesis states that there is a G such that it has good inner product. With all-
Right.
Yeah.
Yeah. No, so like the only thing that I need is that the convex hull of this family should be lower bounded in the norm. That follows from the fact that these all have good inner product with G.
Sorry.
So, for example, if 0 was in the convex hull, then it's not going to happen. So, what I need is a lower bound on the convex hull L2 norm.
Okay.
And that's what I'm deriving from this state.
Okay.
Yeah, so that's the way I want to use it. That's why I phrased it this way. But really, what I want is just a lower bound on the norm.
But what if 0 was in the convex hull? What happens in that case?
Well, in this case, I'll not be able to, like, if I just take the smallest L2 norm vector, that's not going to give me any.
No, the hypothesis won't show because there won't be alpha won't be 0. Yeah. If 0 is in a convex hull, then alpha.
No, but the hypothesis is only about points in F, right? Not in the convex hull.
No, but if 0.
Oh,
then we can.
it's a convex combination only. Okay. Oh, okay.
Sorry, why is the hypothesis false?
I mean, either alpha is negative in that case.
Yeah.
Because.
So, this already implies that 0 can't be in the convex hull.
I mean, the inner product of G with.
So G
Something
has
happened.
between origin and F. That's
Yeah.
basically, that's all. G is
Yeah, so G already ensures that we are far from the.
Separated from
Yeah.
from that.
Yeah, exactly. Yeah. Okay, let's try to use this for codes. We'll embed code word 0 and code words as.
and the required just Cauchy Schwartz.
Yes. Okay, so if I embed all the code words as from 0, 1, plus 1, minus 1, so all the, and I normalize accordingly or just leave the measure so that all the vectors are unit vectors as plus minus 1 vectors. And then the Hamming distances will be exactly captured by inner products. So if the Hamming distance is delta F1, F2, the inner product would be 1 minus the corresponding inner product. And if the Hamming distance is 1 minus beta over 2, which is typically the regime that we work in, that implies that the inner product is precisely beta. This is just translation between the two words. What the Johnson bound says is if the distance was 1 minus beta over 2, then the Johnson bound would be 1 minus square root beta over 2. And this square distinction is precisely coming from the covering lemma, which itself is coming from Cauchy-Schwarz. And it's a simple calculation that this quantity is always between delta over 2 and delta. So as beta is small, the unique decoding radius, which will be 1 minus beta over 4, and 1 minus square root beta over 2, these are particularly different. Like you can approach half with this. For the unique decoding radius, you will never approach half. You can't even exceed 0.25.
So you're going to give a quick proof of
Yes.
the Johnson bound
Yes.
from the covering lemma.
Yes. Okay.
Sorry, what was the point of this slide?
I think he's
So
going
we are just moving to the geometric one. Yeah.
He's going to prove the Johnson bound using the covering lemma. And so he's just stating the Johnson.
So this is just a statement of Johnson bound. Okay, let's prove the Johnson norm. We do the embedding. Having distances correspond to inner product, having balls now correspond to half spaces. And let's say we are trying to bound the list size at j of delta, which is 1 minus square root beta over 2, or in the inner product, it's square root beta. Again, we use the minimum L2 norm guy in this intersection of convex hull and the half space. That's the analog of convex hull of the family F that we had before. This minimum L2 norm R prime can be written as a convex combination of code words because it's in the convex hull. And that can give me some distribution D. What covering lemma says is that this distribution D must satisfy this kind of property. And why is that? Well, what we do know, maybe this should be G, is the received word essentially, chi of R. Let's say R is the received word. So any edge in the list must satisfy this property because it's closer than Johnson bound. It must have large inner product, or in the Hamming distance world, it must have small Hamming distance. Okay. What covering lemma will give me is some R prime such that the square root beta will become beta and R prime will be in the convex hull. And if I just use the fact that R prime corresponded to distribution D, then this is what it would unfold as.
Sorry, I lost the change.
So D is just a distribution on the code words that are closer to the received word.
Yes, yes.
So what is it? I'm trying to figure out what this is.
But in particular, it's over all the codes.
So R prime is some vector in the convex hull.
R prime is some vector in the
So now
convex.
you're thinking of the weights corresponding to the convex combination as giving a probability distribution. Is that what this is?
Yes.
So just want to start with the setup. So we wanted to somehow say that, around any received word, I want to draw a ball of radius j delta. And I want to argue that this ball doesn't have too many code words.
Yes.
Okay. So what you start off with, you say that no, let's pick any. So the family F in the covering lemma is going to be the set of all code words in this ball. Is that right?
Yes. Yes. Actually, you can take the intersection of the convex hull with this entire half space. Even that family works. You can always take a larger family as long as it satisfies the conditions.
Yeah, because in talking about convex hull, it doesn't matter. You take the vertices
So
or
you can always replace the family F by its convex hull. That's not going to change things.
Sure. So, okay. And the hypothesis, the fact that the distance is small, says that this expectation is true. Right? The expectation.
Yes. This one.
Expectation is the conclusion.
Expectation is the conclusion. So this is the thing of. So this is true that H, the list code word,
Oh, I see.
it's close to R.
Okay. Oh, right. You're taking balls of radius j delta.
Yes.
Okay. That gives us that.
Yes. It gives us this.
Okay. And this is something that you know for every edge in your family.
Yes. Every edge in the list.
Right. And therefore, covering lemma says that in fact, if you replace chi of R with some chi of R prime or something, some R prime.
Yeah.
So you have an R prime in the convex hull that has
Yes.
this property.
Yes.
That corresponds to a distribution.
Yes.
Right. Okay.
Okay. And this is all linear, so like you can put it into an expectation. It's not going to change. Okay. What I claim this implies is that the support of D must contain all of these H's. Because if D was full of non-H code words, then those are all far from H. That's the property of the code that we are working on. In particular, the distance of any H prime with H is at least delta. right? So if D did not have H, then this expectation would have to be greater than equal to delta.
I can see that the support of D is a subset of this list, but you're saying that the support
No.
So
Support,
other, he wants to say the other, support contains.
support contains the list.
contains the list.
So think of any H here. Let's say we assume this for now. This is what we concluded. If D did not have H in its support, then the distance with each of the support elements would be at least delta. That's just the code property. It has distance delta. Distance of H from any non-H code word is delta. So on average also it has to be at least delta. So if you're giving me a distribution that has distance less than delta, H better be in the distribution that I'm talking about.
This is why he's using the distance of the code.
Yeah. Okay. The support of D, I can make it small because of Carathéodory theorem, because all of this geometry I'm doing in n dimensions. So I can always pick a distribution, pick a convex combination for this R prime that had small support. And because the support size is small, this size also has to be small. And that's it. This proves the Johnson bound.
So this says something stronger, right? It sort of says that the R prime that you obtain,
Yes.
there could be many
Yes.
convex combinations
Yes.
that you could,
The list is contained in all of them.
all of them. Okay.
Yes.
Huh.
In general, it might be that there are not that many different combinations, but sure. Like if you imagine something in the corner of a body, like some core things will always be there. So
So that's exactly what I was basically trying to get a sense of, does this basically mean that the R prime that you get has to be close to a corner? Because otherwise it somehow feels like, I don't know, if I have a convex body with a lot of vertices,
right,
and my point is somewhere in the middle,
right, yeah,
I can almost avoid any other vertex, right?
Yes.
I can always,
yes,
uh,
yeah,
so it's saying that this should not be possible.
yeah.
But that's basically the statement of Johnson. Because if it's in the middle, it's a convex combination of a huge dice. So those cannot be your receipt word. Your receipt word should be things in which it's a convex combination of only poly and dice. The polytope has exponentially many vertices. But all the R primes that can happen are only things which can, corresponding things can be only poly and dice should be involved.
No, but I think you're saying the same thing, but I'm just stressing the fact that it's not the fact that this can be expressed as a convex combination using poly. The point is, there is only one set of poly things that you can use at all. That's what I'm trying to say.
I don't buy that.
No, because otherwise, if it was the case that, like if you have a large convex body, and there are many ways in which you could express that point R prime as a convex combination of vertices.
There could be many ways of expressing it as 2n vertices.
Yeah, but all of them will share a common list.
Yeah, that's what I'm saying. I mean, you can't have two disjoint sets of supports that give you the same convex combination. Yeah, even though they are small. Saying it's small is not, it's much stronger than that. Because this thing is saying that
You can have these points and
no, but then the result basically says that the thing in the first set that you chose, the list must be contained in that set. The second set you chose, the list must also be contained there. So,
There is a core list. There could be other things on top.
yeah.
This is sort of like, in some sense, it is like in the polynomial, I'm going to make a bit jump. So in the algebraic list decoding thing, you find the polynomial of least degree that interpolates it. There's usually one. If you take the minimum degree, it will divide all the other polynomials that our solution for this. Sometimes it will be the sort of the principal idea, sort of, it's something like that. It's not the same thing, but it's similar. There is one key thing which captures the whole object. Okay, sorry.
Yeah. I'll say more things about the comparison with polynomial based codes, etc. Since we are going to talk about algorithms, this step here, it's not related to algorithmically. This will take exponential time a priori.
By the way, so this one, when you go to the query version and when you go to epsilon away from Johnson mode, it gives you all the corresponding statements of the Johnson mode exactly.
Yes. So for larger alphabet, you can just change this embedding from 1 and -1 to simplex vectors, so that the inner products, when they are same, is 1, when they are different, is -1 over q minus 1.
Basically, everybody is proper roots of unity.
I think so. Just that the inner product is -1.
What is the analog character is still?
No, you don't have to change that. It's only, everything is in R.
Yeah. Oh, it's still in R.
Yeah.
No, but how do you do the embedding then? So if you have larger alphabet, then what is the embedding? In R?
So you just,
There should be.
So you import it or?
Yes. Yeah.
Huh?
Firstly, you embed it in qn dimensions, no?
q minus 1.
Q minus 1 times n.
Yeah, so total n. Let me just tell you for one coordinate.
you import it in Q. Okay, I see.
Yeah, so you increase the dimension of it. And the list size will also increase.
That's
make
what
it less fun.
Johnson mode will be qn or q minus
Yeah,
you will get
Q
n, you get qn or q
Yes.
minus 1 times n.
And for very large alphabet, this will be essentially characteristic.
Can you complete this?
Yeah. So you can just find vectors in q minus 1 dimensions that satisfy this.
Yeah.
Oh, I see.
This is just a PSD matrix. Find any vectors that satisfy this. And this will be sufficient. For q equals 2, this is -1 and 1. Right. So based on this, let me show you an exponential time algorithm that is very
And to answer to this question for the epsilon in this one, you use
approximate.
character.
Yeah. A very roundabout way of doing things in exponential time, because otherwise we'll just enumerate. We first use the covering lemma to find the distribution. And then we sample from this distribution. And basically what you can say is, again, using the distance, that if H was the true code word that I was looking for, I'll find it with some probability. This is just because our final algorithm will be in parallel to this, so I'm putting it out there. We'll come back to this. Okay. Let me also show you the distance proof of Tanner code, because our techniques will be using this. Okay. So remember that the expression that we are going for, if the inner code distance is delta 0, we are going for 0 delta 0 minus 1. So let's say F and G are two code words that satisfy all the local checks. And I'm not putting any condition saying that F and G are not equal. They could potentially be equal. Let me just write down the expressions, and then being equal will come out of the conditions. What is true is, if I look at the distances in the edge space, if F and G are different along some left vertex, then we know that they are different in at least delta 0 d many positions. That's the distance of the local code. And if you do the fractional version, d will go away and it will just be delta 0 times how many times F and G are different according to a left vertex. Right? And let me just call those expressions as delta E and delta L. It's just left distance and edge distance. Likewise, you can make the same argument with delta E and delta R. It's nothing special about left and R. And you can take their geometric mean. Let me call that delta LR. It is true for both, so it's particularly true for the geometric mean. Okay. This is one expression. It's a lower bound on the edge distance in terms of delta LR. I'll give an upper bound on the edge distance in terms of delta LR next. And one of the key steps that we will use is this inequality just about indicators. So if E is an edge and L and R are its left and right endpoints, then if F and G are not equal on the edge E, then F and G are also not equal on the vertex L, F and G are also not equal on the vertex R. What this allows us to do is to, when we are looking at edge distance, it allows us to split it into a product of functions on left vertices and right vertices. And then we can apply expander mixing lemma because it's a function on left vertices, right vertices. So the first step is expander mixing lemma. We went from all edges to all pairs L and R.
What FE I follow? FE is just the.
So F.
The F and G are two functions on the edge.
F and G are two functions.
So F sub to T and G sub to T I follow.
Yes.
What is F sub to L?
It's the entire D bit
The
string.
entire D.
Yes, yes. So when I say they are not equal, even if they are not equal in one position, I count that.
FL is not, those are not, that equality is not between bits, it's between two D bit strings.
Yes, yes. Yeah, so if I was being very proper, I would write F of N of L with the neighborhood, etc. Okay, so now we have this expectation over the edges and one function on left vertices, one function on right vertices. This is where expander mixing lemma comes in. It allows us to write it with an expectation over all LR pairs up to lambda L. So that's the first expression. The second and third expression are just rewriting that in delta L, delta R notation. So this one will just split as a product, true product of delta L, delta R. Second one, because even though it's square, it's just indicators, we just ignore that. They will also become delta L, delta R. This thing, remember, we had called it delta LR. So you get delta LR square, delta LR. You get a quadratic inequality basically. One from the lower bound, like comparing the lower bound and the upper bound. And again, remember, I hadn't assumed F being not equal to G, which is generally how we do code distance proofs. So this is the lower bound and the upper bound. This all in particular, it allows for F being equal to G. So either F and G have distance 0, which is when they are same, or they are far apart. Code distance proofs are quadratic inequalities. And because delta LR is lower bounded, in that case, we can always use delta E lower bound to get back to delta E, because that's our main quantity of interest. We're not interested in delta LR, that's just a surrogate. So this completes the proof of Tanner code distance.
This is the last step was a very weak step. There's a huge law. So
You mean the expander mixing lemma?
no. The expander mixing lemma are all tied.
Yeah.
The last implication which you have
That's the important.
from
The lower LR.
from the delta LR to the delta E.
That's the lower bound.
Yeah, so that's the best lower bound that I know.
Yeah. No. I was just this is related to my previous question at the very beginning. There's this improved decoding of they managed to get. So it's true that they do vertex expansion, but they do vertex expansion. That's vertex they need almost they need expanders all the way up to degree.
Right.
This certainly will not come from spectral.
Right.
But the point is they don't work with the sophisticated Tanner graphs in which you put a code at every vertex.
Right.
They just put the parity.
Yeah.
And they are able to show it. I would believe if their algorithm works for that, it should also work
Right.
for in which you put the parity here. So they don't have a delta knot at all in the base.
Right.
There is only the expansion of the base
Right.
of this one.
Yeah.
And they analyze it only for that. Now, if there's a delta knot,
No, but
morally speaking, this, all these things should be portable even in. Because even Sipser-Spielman, they gave one relation to the base code was parity.
right. Yeah.
They didn't exist such expanders, good enough expanders, so they did these objects and
Right.
these objects existed and.
No, but this one you don't hope for a much better distance proof because there's the complete bipartite graph where lambda is 0 and it's the tensor code. So for that case, you do expect it to be delta 0 square. There it is tight. So there are at least some examples where this will be tight. So
Fair enough. Yeah.
Maybe I'm missing the argument here. So here so we want to give a lower. I mean, like we want to eventually somehow give a bound on delta E of f comma g.
yes.
What we end up obtaining is first a lower bound on delta LR
Yes.
of f comma g,
Yes.
provided f and g are different.
Yes.
Right.
Yes.
So that,
Either f and g are same or there is a lower bound on delta LR.
okay, and delta L. And I presume the last point you were making is that if, for example, if you're working with a complete bipartite graph, then delta E and delta LR are the same.
No, I was just trying to say that for complete bipartite graph, lambda will be 0.
So what will delta E and delta LR look like? I mean,
I wasn't thinking of that here. I was just trying to say that for complete bipartite graph, the true distance is this.
yeah,
So you don't expect a lot of.
no, but I was just wondering what would delta LR be in that case?
The lower one would be tied in that.
The lower bound is
If
tight.
this edge is different, then of course this LR.
Yeah. Okay. I see. Okay.
Yes.
The lower one would be like that.
It can be more different, but yeah. But it wouldn't be tight, right? Like this is always true. If the code has more distance, like they might be different, but the difference extent might be like 2 delta 0 instead of just delta 0. For tightness, you will have to claim that it's close to delta 0. So I think saying that it is tight will require some extra argument. Right? Because they can be different and like way more different. Okay. We showed the entirety of the proof because like our approach also is very similar and we'll see where we have to be different. So if we go, okay, let me tell you about the continuous relaxation that we use for finding the minimum norm guide that makes the problem tractable. Previously, remember that we were thinking of code words as 0-1 assignments to edges, such that each check here was in C0. Now what I'll say is, let me allow distributions for these vertices. In the sense that this vertex might now see a distribution over 3 code words, all of them are still in C0. Because D is constant, I can keep track of all these code words and precise weights and so on. Okay, so now on the edges, this distribution will not give some 0-1 value, it will induce marginals. So if these 3 had weight 1/3, 1/3, 1/3, the first coordinate will get a value of 0.33 from the right hand side because there are 2 zeros and 1 1. Likewise, the second one will also change to 0.67. So every edge will be suggested a marginal from right side, every edge will be suggested a marginal from the left side. And what we ask is that these marginals be consistent. And a small LP is sufficient to write all of this. Just keep a variable for the weight of each small little code word in C0 and ensure marginal consistency. So this vertex might also now have a distribution over 2 guys, and accordingly the marginals will change to 0.5. That's it. So what we overall get is an ensemble of distributions, one for each left vertex, one for each right vertex, with consistency along edges. And this was the relaxation that was used for LP decoding before. What you did was you wrote this relaxation, called for the nearest answer according to this relaxation, and hoped that it was integral. And in fact, like there are proofs that say that using dual certificates, etc., that in up to distance over 4 or something, you can get back the right code word that you started from.
The unique decoding.
This is the unique decoding regime. What we use is the strengthening of this relaxation based on SOS. I'll mention the exact strengthening that we use based on what breaks down when we try to do the proof. We'll see exactly why we need a strengthening of this. And this entire thing, I'll call it a pseudocodeword. So remember that if I had a true distribution over code words, they will imply these local ensembles. But not every local ensemble will correspond to a true distribution. You can always infer an ensemble of distribution from a true distribution. In particular, they are just the marginal distributions of a true distribution. Okay.
So the strengthening would be just asking, here you are just checking the consistency along the edges. Strengthening would be like checking consistency over.
Yeah, so we'll use higher degree SOS. And when you use SOS, there's all sorts of consistency automatically.
And that is strengthening that you're doing.
There are two things, I'll come back to it. Let's try to do this distance proof. So again, remember that because we have these ensemble of distributions, we can at least write down what the value of a small low degree polynomial will be. Like if I ask for a function on, let's say, just these 4 edges here, we can use the local distribution here to answer what the value of that function will be. So low degree functions, and like once you handle low degree, a polynomial that depends only on small number of variables, you can extend it via linearity to low degree polynomials as well. So those things are okay. So let me just talk of distance from 0.
By the word pseudocode, you just need a bunch of partial, marginal distributions, which do not necessarily live to a global distribution.
Yes, that's why pseudo.
Okay.
Let's try to do distance proof for the pseudo code word and see what breaks down. So first we had the lower bound step where we said that
what does this even mean? So I give you 2 pseudo code words.
Let's say one of them is 0. All integral code words are pseudo code words. So in particular, let's fix one of them to be 0 to make our life easier.
So I'll give you a non-zero pseudo code word.
Yes.
And you want to ask the minimum weight distance or whatever.
Yes.
So ask the expectation of E, is that the quantity you want to grow more?
Yes. So previously there was no E tilde. I was doing exactly this.
Okay.
Now there are distributions, local distributions that I need to ask this from. Okay. So I will have this extra E tilde everywhere. But other than that, this is pretty much what we were doing.
But I don't even pass the first. The expectation of E I follow.
Yes.
Expectation of tilde, what does that mean?
Words are not fixed. The distribution on the code.
Yeah, so you think of this function, whether it is 0 or not, you have a local distribution for every edge.
I have a local distribution for every vertex.
Okay, so you have it for vertex, that in particular induces a distribution for the edge.
Okay.
And these are consistent.
Okay.
So you answer what the value of this function should be according to that distribution. And the whole point of consistency is that it doesn't matter whether you do it from the left side, right side, wherever.
Okay.
So you can talk of any functions on left neighborhoods, right neighborhoods, and edges. Okay. This first step is just using that if I'm counting things on the edges, I might as well count things from the left and lower bounded by delta 0. They're different. They're different in delta 0, d many positions. These things still hold true because our distributions are still supported on C0. Okay, again, like you can say the same thing for right side, you can take its geometric mean, all these things are still true. Just going back to the same thing. So the first part, the lower bound is still pretty much same. We didn't do much. The second part that will be trickier. Let's go for the second part. So remember, first step was to bound this indicator function, which still holds true because it's just true as indicators. The second step was expand the mixing lemma. Why should this still be true? It's not clear.
Second, so what's the, so you go from N, okay.
Yeah, so I went from L being adjacent to all pairs, which was
Because you don't have it as a product of two functions, that's the whole issue.
yeah, but that's the next issue. Even if I did get that, how do I break it into a product of functions? Because E tilde of something is a weird thing, like why should that break into product? When there was no E tilde, this was a trivial step. These are both issues.
Well, the very first step, the first step is the EML step, no? Which
Yes.
is the first step, I don't know. Yeah.
But I'll have to argue why EML should work here
Yeah.
with these local distributions, etc.
Right, yeah.
So both of these need some resolution. And the EML step, it's even not clear for true distributions, right? Like why should that, like forget about E tilde. If I had a true distribution, there it is indeed true and it is based on the PSD-ness of the moment matrix, which is always true for true distributions. So it's a PSD condition. We can just add that to the pseudocode that we are asking. And the second condition will use certain low correlation. Like this is just a correlation condition. When you break one expectation into product of two expectations, it's some average case correlation under this L comma R all pairs. So these are the two things that will require us to strengthen our relaxation.
So if you didn't need this expander, then you would have just used the
LP. I would have just used the LP.
and
Then I wouldn't need SOS or so. The strengthening is I enforce the positive semi-definiteness of the global matrix. Still a convex constraint, so I can do that. And this allows me to do the EML step. And I asked that these distributions were actually coming from some much larger degree ensemble. And this will help me reduce the correlation. So, like as we were saying, if we have any two functions, what EML would allow us to do up to lambda error is to change two functions on left and right, change the measure from L and R being adjacent to L and R being independent. And the low correlation will allow us to do the splitting of pseudo expectation to product of pseudo expectations. This one uses PSD-ness, or in the proof compensative view, non-negativity of low degree polynomials. And then the second step uses low average correlation that we'll get by random condition. Okay, so why does random conditioning help with this breaking expectation into product of expectations? Doesn't seem like a very common algorithmic idea except in this one. So what is the main issue? Suppose these two quantities were different. And note that we have already made the EML step. So everything here is with L comma R measure, all pairs L and R. So suppose this and this were indeed different. This just means that these have, like this E tildes have a large correlation. And if they're correlated on average, if I were to randomly condition on one of the right vertices, that would reduce the variance of the left distributions. So if you have two distributions that are correlated, you condition one of them, the variance of the other one goes down significantly. So if the correlation was more than eta, then this average variance would go down by omega of eta square. It's similar to saying that if vectors are correlated, you project them to, and that reduces the norm. Project them orthogonal to the other. So after 1 over eta square conditioning, this can't go on. This eta square decrease in variance. Variance is bounded. So at some point, it must be that this is low correlation. And these are all constant. So eta will be some constant. Is all okay to do. As long as my degree was large enough. So the ensemble was induced by much larger degree moments. By much larger, I mean how many times I have to condition, basically. Then I can afford to condition this. Just like a true distribution, I can afford to condition it n times. If I have the ensemble being induced by larger degree moments, I can afford to condition it many times. But it's still constant, so I'm okay with that. This eta will be epsilon square finally in that one. So that explains the n to the 1 over epsilon to the 4th n. So I'll finally mention the algorithm. Remember that the exponential time algorithm looked like this, that we found the covering lemma, we sample from this distribution and use distance of C to complete. I'll just rewrite this exponential time algorithm as instead of sampling, it's conditioning 1 by 1. One way of saying sampling is to condition 1 by 1, all n coordinates. Right? And distance of C is just this quadratic inequality. In particular, implies this quadratic inequality. And final conclusion is that their distance is 0. The polynomial time algorithm will be, we again find it using minimizing the L2 norm, but instead of finding a true distribution, we find a pseudo distribution. Which has this property that we saw before, that it is closed on average. We condition instead of all n coordinates, we condition on some random 1 over eta square coordinates. And the proof that I showed you with these modifications will give you up to this eta error, a similar proof. The EML step will be lossless because I just enforce PSDness. Only eta will cause an error. And with this quadratic inequality, I can conclude that H prime and H will be order eta close. It won't be 0 like in the exponential case. But I have unique decoders available here, so I can just get rid of the final eta error very quickly. You can just round it. So finally, I unique decode from H. This took time, the first step itself took time exponential. And here we can do this in n to the 1 over eta square because that's the degree of SOS that we go for. So let me quickly talk about some extensions. So this was all Tanner code. There's a different distance amplification scheme of Alon-Edmonds-Luby, where we start with some high rate positive distance code. And with the aerial amplification, we can get rate r distance 1 minus r minus gamma, where gamma is arbitrarily small. And we pay the cost per gamma in the alphabet. So you get near MDS codes starting from any high rate code. So for example, if you started with this high rate code being LDPC, you get near MDS LDPC codes. And what we can show is that this can be made, like this amplification can be augmented with an algorithm that works up to the Johnson bound. Assuming that the C base can be decoded up to some positive constant distance. And we can deal with higher alphabet variants such as this recovery, weighted this recovery. And so for particularly relevant for AEL, we can also do concatenated code, but up to the true Johnson bound, because this doesn't go via list recovery. What you can do is you can directly embed the concatenated part into Rn. So for large alphabet, we would be embedding characteristic vectors, but after concatenation, they would be back to +1 -1. So if you directly change that embedding in the first place and then minimize the L2 norm, that directly leads to Johnson bound of the concatenated code. This is different from how concatenated codes are decoded in Reed, Solomon, etc., where you have to rely on list recovery. Okay, I don't have time for AEL, so maybe I'll skip this. Okay, since some of you are interested, I'll talk a bit more about the Guruswami-Sudan list decoder. So in both cases, we start with some received word and we learn a structured proxy for the received word. In the Guruswami-Sudan case, it's a interpolation, bivariate interpolation. And here it's discovering lemma edge that we had. And then you forget about the received word and extract the list out of this structured proxy that we learned. And to get to the true Johnson bound, in both of these cases, we have to rely on some non-flat distribution or where the weights can be arbitrary. If you are just relying on flat distributions, then you can't get to the true Johnson bound. Similarly, in Guruswami-Sudan as well, you have to rely on multiplicities to get to the true Johnson bound. There are differences as well. Of course, running time is very different. For extensions to concatenated codes, our machinery directly by minimizing L2 norm of the concatenated code word can get to the true Johnson bound of the product distance. Whereas Guruswami-Sudan has to rely on list recovery, which does not yield the direct sharp parameters. And the main question is, like, can we go beyond Johnson bound with this framework? Of course, this has been done for Guruswami-Sudan with folded Reed Solomon codes. One of the future directions is, of course, beyond Johnson bound. And for combinatorial questions, we just have to think about the covering lemma. We don't have to worry about SOS, etc. That's only for algorithmic considerations. And faster algorithms, there are some directions in spectral methods or regularity lemmas, etc. And also for quantum LDPC codes, for which we have some work that is under submission about quantum LDPC codes.
Any further questions? Shashank?
So can it be decoded beyond Johnson bound with ladder code?
Yeah, so we don't know. Like in this machinery, I just don't know of any example where we
No,
can.
but just to prove that the list size is bounded beyond Johnson bound.
We don't know of any such proof. Like we only know up to Johnson bound that the list size is bounded. For all we know, it could be the case that after Johnson bound, immediately the list size is exponential.
But we don't know for sure that this will happen or not.
Yeah, we just don't know anything. It could be polynomial, it could be exponential.
So even if it is polynomial, the algorithm, I mean, you still need that covering lemma sort of proof.
Yeah. So it could be that you have a different proof that the list is small, and this doesn't capture that. So this comes with a list size bound up to the Johnson bound. But yeah.
Why do you compare this to, so you mentioned Guruswami-Sudan, isn't the pattern actually with Sudan's algorithm even before?
Yeah. So I think I was thinking of both of them together. Like
No, the reason I asked this question is why is Guruswami-Sudan important over Sudan? Guruswami-Sudan manages to achieve Johnson radius.
Right.
That was their biggest
Right.
main contribution. But still, I don't think we understand what is it in their technique.
Right.
He lets you hit the Johnson radius.
Right.
It works, the numbers just matter.
Right.
My question would be here there seems to be out there's a Cauchy-Schwarz that's going on for you, which happens in the Johnson radius.
Right.
So is there a corresponding thing? What is the thing that
So it's flat distribution versus non-flat distribution. So you can try to build a regularity decomposition kind of thing, which will always give you a very flat distribution for this covering lemma. So covering lemma in general can have arbitrary weights.
Yes.
What you can do is always have like the weights are not very off from each other. If they are very balanced, then you won't get to the true Johnson bound. You'll be stuck at something similar to Srivastava, which is also the case with Srivastava.
Yeah.
Like all the multiplicities there are one. So
Okay.
yeah, but I'm not fully sure about this correspondence. It just seems intuitively similar, but there's nothing formal about it.
No, the reason I'm asking, I think I don't think we still understand why GS works up to Johnson radius.
Right.
I can give a proof of it. I don't have a what do multiplicities buy?
Right. Right.
Okay. Thanks. Any other questions? Shashank again.